Hello, so I have two presentations today, two short presentations. And the first one is about finding smart ways to guess what users will choose as passwords. And so I have collected a few and benchmarked them against one another. So it will be a lot about Markov models. So hopefully yesterday you had an excellent presentation on the subject, which means I have more time for this slide. So first of all, I'm no mathematician. I have learned mechanics. And worst of all, the only mathematics I know are in French, so I might have all the words wrong, and my terminology might be completely bogus. So do not focus too much on the words, and do not quote me too much. Also, the problem with that is that it might be possible that some of the things I've been doing very difficultly are actually really easy if you know the correct formula or correct algorithm. The other problem with me is that I'm no stranger to disastrous bugs. So as I have more time, I will tell you a little story. So it was the day after Christmas and we all had received a rootkit.com leak. And everybody was eager to find the password because they were really big in the security community. And there was a little problem in that some of the hashes, 75 hashes, were truncated. So it's a bit like a LinkedIn hash, a LinkedIn leak. So I quickly at John the Ripper and produced the correct patch and started cracking. In 3 hours, I recovered 99% of the password. So, it might be a bit strange. And I was very pleased with myself, so I blocked immediately. And then I went to look on the Hashcat channel. And some guy said, hey, look, this sucker, he claims that he broke 99% of the password with a single CPU in 3 hours. It's preposterous. So I was like, yeah, I did it, problem. So I was really happy with myself and was like, yeah, these guys, those big GPUs, but they don't know the first thing about cracking passwords. After a while, someone, I think it was Atom, told me, well, we've been with the guys and we have like lots of GPUs and we're quite used to it. And we cannot crack that many passwords. Are you sure you already cracked that? I said, yeah. Then I thought a bit about it, and there was that really huge bug in my software, so actually I hadn't cracked that many at all, very little, and so I had to edit my blog post immediately, and it was quite embarrassing. So in order not to repeat that, I almost stopped writing C. Now I write Haskell, which is much higher level language, and hopefully there will be not as many errors. Okay. At least all the results in here seems coherent on the first look. It's not like I cracked 99.9% of the password in 3 hours, which is a bit of a telltale. Anyway, also this work is about public leaks, because as I no longer work in the security industry, I cannot have access to customers' passwords and can't have charts like and erase what happened in banks. So I'm going to talk about the Yahoo contributor network leak, which happened a few months ago, and which has a ton of clear text, which makes it extremely good for that kind of test. And every time I will talk about the training set, it will be the Rocky list because it's the best thing ever. Okay, I'm not going to talk a lot about all of this because it's all been covered yesterday. Just perhaps note that my log probabilities are not computed in the same way, so the constant is outside the log, and also it's a negative constant, which means that a very likely event, which will have a probability close to 1, will have a log probability close to 0. And a very unlikely event will have a very high log probability. Also, as we have seen, you can turn multiplication into additions. And perhaps something that is not stated enough about those log probabilities is that having a nice integer is much better for a human than some fractional number, because it's easier to remember, and those of you that have used John the Ripper Markov mode might know what it means to have a level of 200 or 300. It's easy to remember compared to some fractional value. Okay, so what about all those probabilistic models? So it's certain that you have used one, even if you assume some model that, and you didn't realize you assumed it. So the first model is when the probability of occurrence of a character is a constant function. And that is the case of almost all toy crackers, basic brute force, basic rainbow tables, and almost everything that models the password of users like they were randomly picked from a set of characters. More relevant to this talk is the Markov model as implemented currently, which assumes that the probability of occurrence of a character is only a function of the previous character. Okay, so there is also John the Ripper incremental mode, which has been there for a long time, and which is much more complicated of model in the sense that it uses the two previous characters, the current length of the password, and the current position of the character. There is also what I thought was stats, hashcast per position Markov mode, but which turns out to be entirely wrong, so please disregard this line. But what you have to remember for now is that if you can model your probability distribution in a way that only takes into account previous characters or actually state that you already know, then you have a function that gets into that Markov framework and that has really nice properties. So what are we going to do here? I'm going to show some models that are supposed to represent how people choose passwords and generate all the statistics that are associated and use that model to generate candidate passwords. Those candidate passwords must match a certain criteria. So, for example, you can say that every character must be at least as likely as some given value. But what I am going to talk about is when the sum of the probabilities of log probabilities of all characters are less than a certain value. And that's exactly what was explained yesterday, in the sense that it's like you take all the possible passwords and you filter them by the sum of their log probabilities and only take those that are below a certain value. And what's important is that, so the probability of occurrence of the password in log probability is turned to an addition. And this value that I talk about, this threshold, it can be understood as a budget that you spend on individual characters. And that seems to fit well with the way that people choose passwords, because it means that you can either spend your budget in a few high-quality characters, which will be a short random password, or into a long locality password, which will be a password that is long but doesn't look really random, or something in between. Okay, so why did I say that this probability distribution has nice properties? So the first of all is that if you give a certain value, you can quickly compute how many passwords actually are matched by this filter, which means, for example, when I say Markov level 250, I can compute very quickly how many passwords that will be generated by this filter. It's actually possible to compute other values, while it will not be really used in this talk, but you can do all kind of funky things with it. In Markov mode as implemented in John the Ripper, there is actually a maximum length parameter that is also used. In the process of computing that number, you are generating a large structure, which is a graph, and which is called NB part in the paper of the person that I cannot pronounce the name, but the person yesterday told it very well, so I hope you listen to it. And this structure can be then used to compute an arbitrary password. So all the passwords that can be generated in such a way can be ordered, and you can compute an arbitrary password. So this has immediate consequences for rainbow tables, where you can just replace your reduction function, for distributed computing, because you can then cut the search space in even or uneven parts and distribute just the start and end point to the nodes, and then we start tracking. And it also has consequences when, for a general purpose cracker, for example, in John the Ripper, when you press Ctrl+C, you can then resume the computation, and it doesn't ask to recompute all the previous passwords. So, also, what is, I believe, the best thing with it is that for a given plain text, you can compute very quickly its score. And that means that you have a function that goes from a plain text to a score, which means that for any given plain text, you can compute how long you would like to crack it without having to crack it, which is great. And also that you can fill your report with curves, which is great when you're a security consultant, and so everything that comes is a PowerPoint presentation at the end. So here is the kind of curve that you can generate. And I selected a very strange one to show you the kind of things like, it's a bit like CSI, you can have a lot of information with that curve. So this is a huge file that has been distributed by CoreLogic, I think, and it's very strange. So usually, in that kind of curve, it will be a continuous curve with just a single bump, and it will look, well, very regular. In that case, I've graphed the number of passwords on the vertical axis by the score of the password on the horizontal axis. And, okay, I'm sorry, I wanted to do that, I so can't do it. Okay. So here is a discontinuity, which can be explained, because in order to compute this, I had to get a plain text, and so in order to get a plain text, I did run some world list attack, and also Markov attack level 290. So here you have a drop at exactly 290, which is expected because I computed all the passwords that are on the left of this point, and none that are on the right. The password you see here have been found by world list mode. Alright? There are also several hubs, like here and here. And this is most probably because several sources have been aggregated. In usual organization, you will have a single hub, and several organizations will have the hub at a different place. And also that's very interesting, I believe. But what is really strange is here. There is a discontinuity here, and a huge peak here that is much higher than it should be. It drops at exactly level 250, which is a nice round number, and is also the default value for Markov mode in John the Ripper, which led me to believe that some of the passwords were actually generated with Markov mode. So that's pretty cool, right? You can say a lot of things about it. Okay, so now I'm going to, by the way, when does it stop?
You're actually last speaker, so you can continue until everyone has left the room.
So I'm going to give you all excruciating details about how to compute that. Well, okay, so very quickly, I'm going to give you an example of how you compute this structure, because it's not obvious when reading the literature why it works. So in that case, I will use default John the Ripper mode, Markov mode, And I will have several terms. One of them will be the reduced state, which will be the previous character, and which is actually the only information you need to know the probability distribution of the current character. Also the full state, which will be the reduced state, which is the previous character, and the budget you have left to spend, and the next budget you have to spend. So, for example, you can start with a full state of the empty set, because you do not have any previous character, a budget of 100 and 10 characters length. In my example, the training set, which is the dictionary that you use to compute a statistic, will be only those 4 words. So what we are going to do is to realize that this can be modeled as a state machine, and so we will take advantage of the graph structure and exploit collisions in the nodes. Okay, not that important. So here are the probabilities that can be computed from the previous one, so it's not too important, except perhaps just notice that we have 2 words starting with A, and a single word starting with B, and a single word starting with C. So the probability, the cost of starting with the A is twice as low as starting with another letter. So this kind of illustrates what it means that when a character costs more. So you can model that as a state machine, which is, for example, you start at the 0 state, and if you want to start with a C, you will have to pay 13 units of whatever you want. But if you wanted to start with an A, you would have to pay 6. And once you have an A, you can have another A if you pay 9. Is that clear? Okay, I hope. So, what is interesting with that is, for example, well, if you start with a budget of 100, a length of 10, and you get a list of possible next steps, which is written just here. And let's say you take A, then your next state is going to be, full state, is going to be A, because it will be the previous character, 94, which will be the budget you have left to spend, and 9, which will be the next budget you have left. And you will store that in a tree, in a graph, and continue until you don't have any budget, and do that recursively until everything is filled. Well, what is interesting in this algorithm is that the filter would generate 58,000 passwords, but the structure will only hold 621 nodes, which will be, well, it will be orders of magnitude less nodes. I'm certain somebody can compute that and maybe will say, hey, it's log or something, but I have no clue. So here is a graphical example of all the full state trees that we are able to compute. So actually, it's not true at all. So we will start with an initial state with no previous character, because it's the first character, a budget of 20 points and 4 of length. So we'll start with a C, which costs 13. So the next node will be C with a budget of 7 and a length of 3. Okay, we can also have another C. So up, A. So here we have exhausted all the budgets for C. So we start again with the initial node and generate the next node. And what is interesting here is that actually my next choice will collide, and I will not have to compute all the subsequent items in the graph, and that's where the optimization is. So it's pretty nice, but not perhaps that interesting to you. So, okay, so that is what is currently in John the Ripper. So I wanted for a while, since I've read the MathVR thesis, to implement something a bit different that would exploit password structure. And this is not an incredibly new technique because it's fairly well known. As I said, I took the idea from MathVR, and it's actually exactly what you do when you are using hashcat in mask mode. Because when you are saying, I want to crack a password that is 4 lowercase characters and then 3 digits, you are actually saying, yes, there is a high probability that people are picking passwords that are made of 4 lowercase characters and 3 digits. So in that case, in the model, I will say that passwords are made of subsequent parts of a specific character class. I will have 4 character classes, which is lowercase letter, uppercase letters, digits, and everything else will be classified as special character. So you can model that as Markov something. And here is an example for the password pass123. You can say that the structure is either a list of part of class type. For example, it's lower followed by digits, which will be the model that I call no length because I do not record the length information. And surprisingly, the next model is a model with length, which is a list of character classes along with the corresponding length. So in the case of pass123, it's 4 lowercase characters and 3 digits. All right? And here the idea is that I can compute the score of each subpart just as I did previously in the classical Markov mod. And I can also compute the score of the structure in exactly the same way. Because, well, that's the point of Markov mod is that actually you can compute probability distribution. When you have a probability distribution of subsequent items, you can apply it. So in that case, it doesn't have to be a character. Here, I can also do it with a structure. And also, I have added a constant, which is b. And why did I do that? Because I had the intuition that the structure was more important than the individual parts. So somehow I had to represent that in some way. But, well, in this work, that value b will vary, it will be an integer, and will be between 1 and 6. But I later realized that it should have been a much better idea to have a fractional b from 0 to 1. Well, when? Anyway, so in order to compute NB parts, for that case, it's much more complicated. I will not bother you with it. Well, I hope my results are exact. So here is the main loop. It's not obvious. It could have been written in a much more obvious and elegant way. Unfortunately, there would have been horrible performances and especially memory usage, so would not be computable. So I hope there is no bug in it. It does seem to be pretty coherent, so I'm not too worried. Okay, I'm now going to list the different types of probabilistic password generators that are benchmarked. So the first one will be frequency optimized brute force or exhaustive search. So think of the most basic brute force mode you can have, which is computing all passwords starting from password of length 1 to password of, well, arbitrary length, and by using all characters from a specific char set. So that's exactly what it is, except the letters in the char set are sorted by probability of occurrence. And what we should wonder is what is the optimal char set length in our case. So I did the computation for several values, and it turned out to me that it was 36, which turns out to be the set of lowercase characters and digits, which matches quite well the observations that you should have when cracking passwords. And, well, perhaps a bit about these curves. So there will be those curves till the end now. So it's curves of percentage of cracked password by password tried. So the horizontal axis is a logarithmic scale, and it means that I will mainly focus on what happens around here. The reason for that is that here you can see types. So the first number is the number of tested password. The second number, as I will explain just after, is how long it takes to test that many passwords for a fast hash on a decent video card. So after 5 years, I believe, well, even if you have 25 cards, it still takes a huge amount of time. So I will mostly focus about this point, because, well, obviously, if you have infinite time, you better use the full char set, because you will actually find all the passwords. But in the given time frame, it was 36 and 1. Okay, so a bit about the notation. For all the Markov modes I tested, you will have a value which will be the model structure slash the subpart slash the b-value, where the two first parameters will be either m1 or m2, which is Markov using the first previous character, or Markov using the two previous characters. The model type will be no model. In that case, it will be a Markov mode just like John the Ripper, without taking into account password structure and just characters. There will be also the model with type and length, and the model with just type. And the b-value, as explained, will vary from 1 to 6. So, for example, when I write M2, M2, P2, it means, okay, well, you are not interested in that, you want to see which card most password, right? So, I also benchmarked word list and mailing rules. I will talk a lot more about this in the presentation just after. But, well, I use a good word list, a good mailing rules, and two word lists, one being Wikipedia Esrabo, which you have heard about, and the other being Roku. So, a word about also all the script is that, okay, I have graphed password found by password tried, but what you are actually interested in is password found by time spent. And this I haven't graphed. Also, in the case of word list, and especially mailing rules, as I will explain later, there are mailing rules that are smart enough to discard some of the password. So some of the password will never be tried. So mailing rules, here I have just graphed size of the dictionary times number of rules tested. So it should be more effective in practice than shown on the graphs. And a quick note also about the axis and also order of magnitude of cracking time. So you will see the first number is what happens when you use UCL hashcat cracking a 100 kilo password of fast MD5. So it's pretty fast. The other value, which is somehow very interesting, is when attacking a decent hash system such as bcrypt, which is not faster, not really faster on GPU than on CPU. So in that case, it is attacked with a dual Xeon CPU, which is pretty fast. And so as you can see, something that you can do in no time at all, at 10 at the power of 11 with hashcat and MD5 takes forever with a decent hash system. Okay, so I did all the comparisons. So the graphs here are not really readable. If you want to check them, you will be able to download the slide and zoom in, so it's all vectorial, there is no problem with that. But in the end, I selected the best performing system for each different probabilistic model. So in that case, what I found is that for part type only, which is when I model the password structure while discarding the length of each part, is that the best performing model was when I used a simple Markov model for the structure and a 3-gram password model for each subpart, and also with a constant of 2. Same thing for part type and length. So here is about the same story, except the constant has a value of 1. And I also benchmarked John the Ripper incremental mode. There are quite a few curves, and it's pretty interesting in the behavior of the statistical generator. So there are two kinds of statistics here. One of them is called standard, and it's what is shipped with John the Ripper, and one of them is called contest, and that's what we used during the cracking if you can contest. And what is interesting here is that you see two curves, the two winning curves are actually pretty much the same. And in one of them I only use alphanumerical values, and in the other I use all possible characters, which means that the model is trained to be, well, it seems that the alphanumerical model is almost optimal, and the all character model trained so that it's almost identical. Okay, so here is the result. You can see something I did not talk about, which is the stats processor that is a standalone program from Team Ashcat. So I also tried a lot of values for a few million characters and selected the threshold that would give me the best results. So in that case it was 20, but as contrary to the Markov values, I can't really compute how long it would take to crack a given password using this method, which means that I actually ran the cracking, well, I did crack the password using it and just looked at how many were cracked. So I selected its values and cracked for a few millions more and did the graph. And so the graph, something are interesting and something are pretty obvious. First of all, well, wordless mode wins every time. It's the most efficient way to crack passwords. Only it's doing those after a while in the sense that you do not have any more rules. Or you can add random rules, but it will suck. So in that case, there are quite a lot of rules, and I will talk more about it later. Also, there you will see... okay, so the blue round is also using wordless, but with a less effective dictionary, which is the old Wikipedia Estrago. So I hope the next one will be much more effective. So, and what is interesting here is the winners, which I believe would be those two modes, which are, well, row MT2 for the blue one, which is, well, just like plain old John the Ripper Markov mode, except using two characters, so 3 grams. And the other one is when using password structure. And the sub-model here, which is using the password structure without using number, totally sucks, so it's to be discarded. Also, well, about this curve, as you have seen yesterday, in John the Ripper, the way it is implemented, you have to set a level. For example, I say this level, and it will compute all passwords until this level and will stop. And the curve, if you do that, will look more like that. Nice. And well, in order to overcome this problem, you have to implement it the way they did, which is actually computing the password in optimal order, which would be exactly that curve if you do it right. And also, incremental mode for John the Ripper, it's a gray value that's here, which is much better than brute force, which is here with the typical staircase form. Okay. But this doesn't tell the whole story. When you start cracking with Markov mode with fast hashes, even on CPU, you will notice a very, well, noticeable slowdown, because it's extremely expensive to compute these hashes. So obviously, stats processor computes them much, much faster. And, well, obviously I did not optimize as well as I could. So perhaps there are gains to have, but what is important is that it all depends on your target. When computing on a GPU, you cannot use for fast hashes slow algorithm even if it's very effective, because, well, perhaps in the same amount of this password I have cracked 10% more passwords, but perhaps a GPU will run 100 times faster, so will actually crack the same or more passwords. So it's actually pretty difficult to compare, except that to notice that some ways of computing these password candidates are much more smarter than others. Okay, and also this curve, actually nobody cares about it, because nobody cracks like that. Usually what you do is that you start with your word list, and you remove all the easy passwords, and then you try the more complicated stuff. So that's exactly what I did. I ran, well, a huge word list with, at the same time, YouTube and Wikipedia with a lot of rules. I removed all the bad passwords. I also ran the old Markov mode at default level, and that means I only have now 28% of the original password. So in that case, it's much more interesting, because well, you can see that the mode without password structure seems to be more effective at the beginning, but then with password structure you see gains at the end, which I expected would be the other way around. The reason for that is that without password structure it's more generalistic, so it should crack more complicated password than the other mode, which might be overfitted to a specific model. So here is my research for this, and it seems that these new models are much, much stronger, so they will definitely go into John the Ripper. The new model with password structure is nice. I do not know how easy it will be to implement it so that it's not too slow, so it will be some hard work. It should also be seen that all of those modes are next to useless when you only can test a few passwords, which means that for the very slow hashes, well, you just use word list. Also, I need some benchmarks, because I'm pretty certain now that fractional values of B would be much more effective, and the model will be better tuned that way. Also, there are things that I cannot answer today. So what about implementation speed? As I said, it's significantly more complicated than other models, so it might be too slow to be actually useful. How does it fare against Hashcat brute force ++? In theory, brute force ++ should be less effective than stats processor. But in practice, it's much faster because it's on GPU. And also, I'm pretty sure I did not do things properly with stats processor, so it's a guessing game. So soon I will add at least raw Markov for trigrams in John the Ripper, possibly with the good algorithm that will let you try password in optimal order. Perhaps a rainbow table implementation should be added, so I will look at it because it lends itself very well to rainbow tables, I suppose. Okay, that's for the first presentation, right? Or the two?
This is actually for two, but...
Okay, so, and, okay, questions?